How do computers remember? I'm not gonna do an intro or anything, let's get straight into it. Let's take a dive into the concept of loops and logic gates or loop errors. If I were to plug this back into itself by using a delay, then we can see that it sort of saves its on position. But we also want to be able to turn it off, so we can introduce an AND gate to that. I'll make this an AND gate, plug the OR into there and have it cycle like this I have on screen. And also plugging in input B into the AND gate. Now if input B is on and input A is on, then it saves a value. But I don't like how we have to keep on input B to keep a value saved. So we can introduce a NOT gate. Now if we plug in switch B into the NOT gate and plug in the NOT gate into the AND, where it cycles like this, what this is doing is allowing it to save the value and then allowing us to reset the value when we press the bottom switch. We can also just delete the delay and loop the AND gate back into the OR. This allows us to save and then reset it. What we have created is a SR latch, or a save and reset latch, where the top one is saving and the bottom one is resetting. I'll go ahead and make some visuals for my visual learners. So when the top one is pressed, then it would save. And now when the bottom one is pressed, it would reset. We could sort of formulate this into a equation where Q being our save value or output value, S or Q and not reset would equal our output value. The Q would be plugged into itself, of course, in this situation. We could sort of simplify this by using two NOR gates. If you see here, if you plug the NOR gate into the top one, then it would turn it off. This would allow us to loop it back down without it interfering with the output value. Just like in the equation, we have two outputs, Q and not Q, or Q bar. If it's not obvious enough, Q bar is basically the inverted output of whatever's on top. What we have made is a SR latch utilizing the NOR gates, which is a little bit more faster when it comes to high processing logic. Now, why did it just make two different types of latches? Well, other than complexity of the amounts of gates used, sometimes there's going to be something called gate delay. Some people don't teach this in their videos, but I feel like it's really important. There's a tiny amount of time, usually measured in picoseconds or nanoseconds. Gate delay is like the tiny amount of time it takes for a logic gate's output to change after we press an input. Now, this would be very noticeable inside Build a Boat for Treasure because the tick rate is very low inside Roblox. But in real life, it's not going to be that noticeable. Now, in Build a Boat for Treasure or in real life, it matters because it limits the CPU speed of whatever you make. Let's say in real life, people are passing around a bucket of water down a line to put out a fire. When the first person gets the signal to start the input, it takes a few seconds for them to pick up the bucket, turn around, and hand it to the next person, which could be the output of the first gate. This lag between receiving and passing the bucket is what we could usually think of gate delay. And because of different pathways in a circuit that have different gate delays, signals can sometimes glitch, have conflicts with one another, and have momentarily blips in the output that can mess up your CPU entirely. We can talk more about this in another episode. Now, if we were to save a value, then reset at the same time, this would bring us to an invalid state. This would start to happen a lot at very volatile speeds or high tick rates. If you want a more better mechanism, it would require more logic and it would allow us to specify if whether a 1 or 0 should be saved. Let's say we have two switches, one is for value and one is for saving. Let's say I want to be able to save a 1 when saving is on. We can say something like, if save and value is on, then it should turn the bit into a 1. Let's also plug in the AND gate into the bottom NOR latch right here. Now if value and save is on, then it changes the output into a 1. Now what if value is 0 and we want to be able to save it? We just have to say save and not value, which is 0, would mean that it would reset the latch. So let's add in a AND gate, and let's also add in a NOT gate right here. Now let's plug this into the reset. So if it is not value or a 0, and we press save, then the output should turn into a 0. And if there is a value and we press save, then the saved output turns into a 1. This is commonly known as a data latch, and also this latch-based approach to memory is commonly only found in small memory chips. Even though it's fast, it takes up a lot of space. We typically use something called capacitor memory. I'll talk more about dynamic memory in another episode. Let's go back to the subject of gate delay. Let's say we're saving a value, and then all of a sudden, due to some form of delay, when we tell it to stop, we could imagine the value would shut off before the save, ultimately making the value turn into a 0 instead of the value we wanted. This happens because, for one, delay, and also because the circuit's asynchronous. And to make it synchronous, we're going to have to introduce something called the clock. Let's try to visualize this to have a deeper understanding. This line is to represent when it saves. Let's duplicate this, and let's say that this is the value that we're going to be saving. And let's say due to some form of decoder or multiplexer causing it to have some form of delay, we'll extend the save just by a little bit. Now in this situation, we can see that it would turn into a 0 right as soon as the save is about to turn into a low. Now what is the most obvious approach to this? Well, to save sooner, or to just save at the rising edge. And to do this, we'd have to make something that just pulses once it's turned on. I'm going to replace the levers with some OR gates just to have some better organization. I'm also going to shrink this by a little bit just to make this a little bit more compact, you know, look a little bit more nicer. So our initial idea is to just use a NOT and a AND gate, but sometimes this would break. I mean, you could technically use this if you're doing a very low bit build, like a 8-bit computer build. But when you have multiple registers, this can sometimes fail and send more than one pulse, especially when you're past a certain tick rate past 50 Hz. So instead, we're going to make something called a one-shot. A one-shot would only send a pulse when it's at the rising edge. So let's go and take advantage of the fact that there's gate delay in the game. I'm going to use 2 AND gates, 1 NOT gate, and an OR gate. The OR gate up here is just for input organization. I'll plug the red input into these 2 AND gates. I'll then plug in the AND gate into the OR and the OR into the AND gate, and also connect this into the input. I'll also connect the AND into the NOT and then the NOT into the AND gate up here. This will also replace the save input. I'll just drag this over too and organize it just a little bit better. Now with the rising edge data latch, if the value were to suddenly turn off early, now it does not affect it at all. It would only save a value if the clock were to turn on. Let's go and stack this by 4. And now I'm going to connect the save into one singular input. Same with the load. Now to test, let's say you want to save a value of, let's say 3. And I press save, and now it's store the value. Now when I press load, it would then load the stored value. What we have made is a 4-bit register. Now multiplying this by 2 and wiring them again would make this an 8-bit register or a 1-byte register. But for the sake of this video and my own sanity, let's not do that for now. Let's go and bring in an adder from a past episode. This is a basic carry ripple adder. I'm going to plug in the register's output into the adder, and then plug in the adder's output back into the registers. I'll also have the load on always on, and also with the carry in. I'm going to temporarily use the lever as a clock. Every single time the lever becomes a high value, 1 bit will be added as if it's counting upwards. Now, let's go and remove the lever, because turning it off and on is way too tedious. So instead, let's go and make a clock. I'm going to turn this into a NAND gate, and then invert the bit by using an OR gate. Now let's go and place down a delay. I'll plug this into here and loop it back. This should turn on and off repetitively. I'll also set this to whatever tick value I want it to. Now if I were to press the lever, then it would start ticking at my desired speed. What we have made is a counter, which is also commonly used in sequencing when it comes to memory. For example, the step-by-step instructions inside of microprocessors and computer architecture. This is basically what tells the CPU to go through the instructions in memory. This process relies on what we call a program counter, but I'll explain jumps and conditions later on, maybe for another video. But since we're not using any jumps or conditions, let's go and use something called flip-flops to make the counter a little bit easier. This is our register without the load function. Let's go and plug in our Q bar into our value input. Now, if I were to bring out a button, and if I were to press save, then you can see that the value sort of flips. This is a flip-flop circuit. Now dragging this down and then plugging in the Q bar into the save, what we have made is a more simplified clock without having to use an adder. We have went through the basic concepts of loops and latches. For my next video, I might be explaining either how division or multiplication works. And then after that, I'll probably explain how PID control works for the mechanical engineers. Anyways, if you like this video, please subscribe. See y'all and bye.